Determine if each series is convergent or divergent. For the first example, we have the sum from n equals 1 to infinity of 2 pi to the power of n divided by 6 to the power of n plus 1. This may not look like it, but it's a geometric series. To begin, let's write 6 to the power of n plus 1 as 6 times 6 to the power of n. Recall when multiplying and the base is the same, we add the exponents. So we can write this as the sum from n equals 1 to infinity of 2 pi to the power of n, all divided by 6 times 6 to the power of n. Notice in the denominator we still have n plus 1 factors of 6. And now to include a factor of 1 in the numerator. And notice both 2 pi and 6 are raised to the power of n. And therefore we can write this as the sum from n equals 1 to infinity of 1/6 times 2 pi divided by 6 raised to the power of n. And then from here we can simplify inside the parentheses. 2/6 simplifies to 1/3, or there's 1 2 in 2 and 3 2s in 6. Let's consider the series in the form of the sum from n equals 1 to infinity of 1/6 times pi divided by 3 to the power of n. Now it does fit the form we're used to seeing for an infinite geometric series, where notice r, the common ratio, is pi divided by 3. So the common ratio r is equal to pi divided by 3. Recall pi is approximately 3.14, and 3.14 divided by 3 is greater than or equal to 1, and therefore the series is divergent. Recall whenever we have a geometric series, if the absolute value of r is greater than or equal to 1, the series diverges. If the absolute value of r is less than 1, then the series converges, and it converges to a, the first term, divided by 1 minus r. So again, here we know the series is divergent. Let's consider the second example. To begin, let's write the denominator of 16 to the power of n plus 1 as 16 times 16 to the power of n, and consider the sum from n equals 1 to infinity of 4 pi to the power of n divided by the product of 16 and 16 to the power of n. Again, let's include a factor of 1 in the numerator. Notice both 4 pi and 16 are raised to the power of n. Let's write this series as the sum from n equals 1 to infinity of 1/16 times 4 pi divided by 16 raised to the power of n. And again, we can simplify the common ratio r. 4/16 simplifies to 1/4, or there's 1 4 and 4 and 4 4s and 16. Let's write the series as the sum from n equals 1 to infinity of 1/16 times pi divided by 4 raised to the power of n. Notice now we have the common ratio r is equal to pi divided by 4, which again is approximately 3.14 divided by 4, which is less than 1. Because the absolute value of r is less than 1, the series is convergent. Let's also determine what it converges to by determining the infinite sum, which again is equal to the first term a divided by the quantity 1 minus r. So we'll have to determine the first term. In our case, n starts at 1, and therefore the first term is a sub 1. A sub 1 is equal to 1/16 times pi divided by 4 to the first, which equals pi divided by 64. And now we'll determine what the infinite series converges to by determining the infinite sum, which is equal to a sub 1, or pi divided by 64, all divided by 1 minus r, or 1 minus pi divided by 4, which is equal to pi divided by 64, divided by, in the denominator we have 1 minus pi divided by 4, which is 4/4 minus pi fourths, which is the quantity 4 minus pi divided by 4. Instead of dividing, we'll multiply by the reciprocal. This is equal to pi divided by 64 times the reciprocal of 4 minus pi divided by 4, which is 4 divided by 4 minus pi. Notice we have a common factor of 4 between the numerator and denominator. There's 1 4 and 4, and 16 4s and 64. Multiplying, the infinite sum is equal to pi divided by the product of 16 and 4 minus pi, which, if you're curious, is approximately 0.229. This second series converges, and it converges to pi divided by the product of 16 and 4 minus pi. I hope you found this helpful.